Hello, everyone. So welcome to the sixth lecture in topic 5.4. Today, what we'll be doing is basically talk about the forces acting between two current carrying wires. So I have been telling you we'll do this force between two current carrying wires, but until now I have not done so. So today that will be our main task. But before that, what we will do is we'll recall a little bit about the magnetic field due to a current carrying wire and the dot and cross notation. And also we'll recall slightly a Fleming's left-hand rule to find the forces. And only after that we'll go to the forces between two current carrying wires. Okay. Now let's start with the magnetic field due to a current carrying wire, straight wire. Okay, so let us assume a current I flowing through this straight wire. So the first observation that we stated last time in the last lecture was basically that the magnetic field of the current carrying wire is basically a circular field. Okay. And how is the directions of the magnetic field? How can we find the directions of the magnetic field? We can find the directions of the magnetic field by using a screw rule. So the screw rule basically tells us that if your thumb is pointing in the direction of the current, the direction of the curl of your finger basically gives you the directions of the field. So in this case, the circular field will have a direction that's clockwise. So the magnetic field of this straight wire is basically clockwise. So that's what we did first, right? And we also said that it's not always easy to draw the 3D image of the magnetic field. So we can put it in a 2D representation of the same thing. So if I want to have a 2D representation of this one, so basically then what I do is I draw a straight wire like this. And let me draw it like this. So let's say this is a straight wire. Now, because the current is flowing in the upward direction like this, okay, so this is I, let's say. So it's moving in the upward direction, the current. So again, the dot and cross notations for the magnetic field is this. If you draw a cross, it means that the magnetic field is moving away from you. And if you draw a dot, the magnetic field is coming towards you. So in this case, again, I point my thumb upwards, right? Because the current is in that direction. And if I look at it, on the right side, I go inside. Okay, on the right part of the wire, I have to go inside. So because my finger is curling inside, right? So for that, I have to draw a cross here. Okay, it's just a representation that the magnetic field is flowing inside. So I draw a cross here. And as you can see, from the left side, the magnetic field is coming out of the page. So I just draw it as a dot. So on this plain paper, I know that the magnetic field on the right side is going inward, and to the left side of the wire, the magnetic field is coming outward. So this is the dot and cross representation of a magnetic field of a straight wire, of a current magnetic field of the current carrying straight wire. Okay, now again, I also told you all that you can draw as much dot as you want, as much cross as you want. Okay, like this. So it could be upward like this too. So this is the second thing that we studied. Now, let's talk about the force acting on a current carrying wire if it's placed in the magnetic field. So that's the concept that we need too. Okay. Let us assume that there is a wire that's in between the magnetic field. And also let us say that the current I is flowing through the wire. Now, we can observe here that if you want to find a force, the magnitude of force acting on that particular wire, which is of length L. So let's say this wire has a length of L. Okay. So if you want to find how much force acts on that particular wire, then it's basically given by B I L sine theta. Okay. So that's the formula that you have to remember. So where L is the length of the wire, I is the current flowing through the wire, and B is the magnetic flux density that the wire is placed in. And theta here is basically the angle. Theta is the angle between the direction of the current and the magnetic flux density. Okay, so this is the force formula that we know, right? So now the other thing is, okay, so there is a force acting on that wire, but what about the direction? Where does the wire get pushed towards, right? Is it towards up? Is it towards right, left, down, oblique? So we don't know, right? So for that, we have a rule, and that's called the Fleming's left-hand rule. So Fleming's left-hand rule gives us the direction of the force. Gives us the direction of the force. Now, what it says is basically, if you make a finger perpendicular, if you make your three fingers perpendicular to each other, thumb, index, and the middle finger, if you make it perpendicular, then the index finger, so then the index finger is the direction of the field. Okay, so it's the direction of the field. And the thumb is the direction of the force. And your middle finger is basically the direction of the conventional current. Okay, so basically middle finger is basically the direction of the conventional current. So conventional current means that we're assuming that the positive charge flows. Okay, even in the electrical circuit, like we discussed last time, that conventional current is the standard used in the electrical circuit, okay, which we assume as the direction of the current. Now in this case, the finger, the index finger is basically pointing from left to right, right? And the current is flowing inside, so it's inward here. So it's inward. So the direction of the force, you can see the thumb is downward, right? So basically the force acting on the wire is towards downward. So that means if you keep a wire that's perpendicular to the field, the wire gets pushed downwards, okay, with this much force. Okay, so with that, we are done with the revision of the previous lectures. Now let's move on to the main part, which is the forces acting between two current carrying wires. Okay, so let us assume that there is a wire in which a current I1 is flowing through it. Okay, so let us just give a name to this wire. So let's say this is wire 1. So let's say this is wire 1. And maybe let's say there's a current I1 flowing through it. And the field that this wire produces is B1. Okay, so let us assume that this wire has these characteristics. So maybe let's say that I show that the current is flowing in this direction here. So this is current I1 flowing through this wire. Okay, now because we're trying to find the forces between two current carrying wire, let us also draw another wire, which maybe I'll choose a brown color here for the other wire. Excuse me, so let me choose a thicker ink here. So maybe this is the wire 2. Okay, now let's say this is wire 2 here. So oops, this is wire 2. So this is wire 2. And the current flowing through this is I2. And the field that this produces is B2. Okay. So again, the current that I'm showing here is I2 here. And here is I2. Now, let's look at the field, individual magnetic field of these two wires. And then we'll talk about the force. If you look at the black wire, or in this case, the wire 1, we know that the current is flowing in the upward direction. So if I want to find the magnetic field in a dot cross notation, what I do is first I'll check where is the, how is the magnetic field flowing through the current, right? Through the wire. So for that, what I will do is I'll point my thumb towards the direction of the current, and I will curl my finger in such a way that it's the direction of magnetic field. So in this case, the right side has a cross because it's going away from me. So in the right side, I have a cross field. And in the left side, I will have a dot field here like that, because it's coming towards me in the left side, right? So this is the magnetic field pattern of the wire 1. Now you can see that the wire 2 is in the vicinity of the, or let's say in the magnetic field of the, in the magnetic field that's produced by wire 1. So which means we also said that if a current carrying wire is in the magnetic field, then that wire will experience some force. So let's look at the force. So now let's look at the force acting on wire 2 due to wire 1. So this is the notation that I will refer to, okay? So now I'm trying to find a force on wire 2 because of the wire 1. So for this one, what I can say is, okay, because the formula is BIL, so what I can just do is, so I can just write magnetic field, but magnetic field of whose? It's a 1, right? So magnetic field of 1. And I, so I current is the current in the 2. And the length is the length of the wire. That's the length of the wire 2. And sine theta is just sine 90 because it's perpendicular. The direction of the current in the magnetic field is perpendicular, right? So sine 90 is 1. So I'll just write sine 90 so that we don't get confused. So this is the force acting on wire 2 due to wire 1. Okay. So that's the magnitude of the force acting on wire 2 due to wire 1. What about the direction here? So this is the magnitude. What about the direction? Again, we'll use the Fleming's left hand rule. Now, if you see here, the wire 2 is in the field in which my field is pointing downwards, right? It's going away from me. So that means my finger, the index finger, has to point inside of the page. So it's pointing inside of the page. Now, where is the current flowing? So the current is flowing upward because the middle finger represents the current, right? So I have to do up. So if my field is inside, the current is upward. So look at my thumb here. So the thumb is pointing towards the left. So that means the force acting on this wire 2 because of the wire 1 is towards the wire 1. Okay, in the direction towards the wire 1. So I will write like this: force to 1 is given by this. Similarly, we also know that the wire 2 also produces a magnetic field. So we'll do the same analysis for the wire 2, and wire 1 being in the vicinity of the magnetic field of the wire 2. Okay, it's the same process, but we'll now exchange the role. Okay, in the wire 2 also, we see that the current is flowing upward. So on the right side, the field is going inside, right? So on the right side, the field is inside. So I draw a cross here. But on the left side, it's all dot. Okay, so it's dot here. Now, let us try to understand what is the force. Excuse me, let's change the color here. Let's change it to yellow. So force acting on 1 due to 2, due to wire 2. So if you look at the direction of the field, that the black wire is in, you see that it's dot, right? So the dot means the field is coming towards you. So that means you point your finger outside of the page. And now, if you look at the direction of the current, it's upward. Okay, so it's a little difficult to do it, but we can still try it. Okay, so if you look at the thing, it will look something like this. So the field is upward, right? So maybe you can point a finger towards you, and then maybe you can rotate it like this, and the field is pointing upward. Okay, and the current is going upward, and you see that the current is acting towards the force is towards the right side of the towards the right side of the wire. Okay, black wire. So this is f of 1 due to 2. Again, let me say that, right? If your thumb is pointing towards you, now it's a little bit difficult to do it, okay? I mean, if you stand up and do it, it's easier, but if you sit down, it'll be a little difficult. So the thumb is pointing towards you, and the current is going upward. So you'll just put your middle finger up, right? And you see the thumb is pointing towards the right side. So this is the force acting on force acting on 1 due to the current due to the magnetic field produced by the current wire 2. About the magnitude, you see that B, right? So B is produced by the wire 2, because this blue dot and cross is because of the wire 2. So wire 1 is in the magnetic field of wire 2. So B2 times now the current. So the current has to be in the wire 1, right? Because we are looking at the force acting on the wire 1 times L1 times, again, sine of 90 degrees, because the direction of the angle between the direction of the current and the magnetic field is perpendicular, so it should be 90 degrees. So from this case, what we can see is basically that the force acting on the wire 1 and wire 2 is exactly the same. Does it look same? Let's try to verify that. Okay. So now, if you recall, the magnetic field produced by any current carrying wire, if it is a certain distance d, okay, so if this point is d away from the wire, then we know that the magnetic field produced at this point is given by certain formula, right? And let me just write that formula here. So that's B equals to mu naught I over 2 pi d. So this was the formula of the magnetic field at certain distance from the wire. Okay, if we use this formula here, we see that the these two forces that we have found is exactly identical. So B1 is due to wire 1. So the distance is d, right? So the distance between these two wires is d. So I can write here mu naught I1 over 2 pi d times I2 times L2. So which basically gives me mu naught. Let me just write L. Okay, I'm assuming that both the lengths are equal. So L I1 I2 by 2 pi d. So this is the force acting on wire 2 due to 1. Likewise, I can also write here B2 as mu naught I2, okay, divided by 2 pi d times I1. Instead of L1, I'll just write L because I'm assuming both the wires have the same length. And likewise, you have mu naught L I1 I2 by 2 pi d. Now, what is the conclusion here? So the conclusion is basically that if you have two wires in which the current is flowing in the same direction, there is an equal and opposite force acting on each wire. Okay, so there is an equal and opposite force acting on each wire, and the force is basically force on any individual wire is given by mu naught L I1 I2 over 2 pi d. So this is one of the conclusion, and the next conclusion is that the wire tends to attract each other, okay, when the current is flowing in the same direction. So that's the point that you have to remember. Now, likewise, we can also show that if the current is flowing in the opposite direction, then we can say that the wire tends to repel each other. So I leave that as an assignment for you all to verify it. Okay, the analysis is very similar to what we have done here. So I leave that as an assignment for you all to do. And if you have any questions, we can discuss in the class. Okay, so let's do that much for today. I'll see you in the next lecture. Have a nice day. Bye-bye.